So it's my great pleasure to welcome our next speaker, Vijay Reddy, Associate Professor at Harvard University, to talk about Architecture 2.0, prompt engineering, and foundation models for Edge AI hardware design. Thank you, Vijay.
Awesome. Thank you. It's a pleasure being here, folks. So today I'm going to be giving very much an academic talk. What I mean by that is that, I'm trying to think about things that are further out. Like much of the industry folks are kind of talking about what's here, what's happening now. I'm trying to think about where we're going to be going in the future and what are some possible opportunities around this space. And that's what's going to be culminating on Architecture 2.0, which I'll define shortly. Now, I think TinyML is a really interesting ecosystem where we are right now, right? The fusion of all the technology that we have kind of come to is really the remarkable aspects of visions that have been created way back. If you haven't read this article, The Computer for the 21st Century by Mark Reisner, it's a remarkable article which came out in 1991, which kind of talks about this very immersive world that we're going to live in. And in fact, one of the critical elements that they say is that specialized elements of hardware, software connected by wires, radios, infrared will be so ubiquitous that no one will notice their presence. I think the aspect of that no one will notice their presence is exactly what TinyML really is, right? For me, it's like any technology is really, really effective when it basically disappears into the background. Now, that's kind of like the vision that people have had almost since the late 80s, early 90s. And I think we're starting to be able to manifest some of that vision after a few decades of work. However, I think there's a very big sort of a problem that's kind of lurking behind all the excitement that we're all talking about all the time around applications and what's possible. And I think it really kind of comes down to this fundamental question of you got to build these chips, right? TinyML is all about having very low cost sort of devices, having them be everywhere around us and so forth. But the cost of generally building chips has been steadily growing. Now, this is an old document from 2018, which is basically kind of talking about how much does it really sort of cost nowadays to kind of build a chip and where are much of the money really going? Now, this is kind of broadly talking about the large silicon ecosystem, but I think the critical element is that, if you look at each one of these bars, which goes from coming up with IP qualification to designing the architecture to actually verifying it, doing the physical design, then the software that you got to build on it, dealing with all the complexity that comes about it, is basically has been steadily increasing over time, right? Now, this is a really interesting problem for us to be stuck with, because if the cost of building these systems that we really need to be very pervasive keeps going up, then it begs the question of how are we actually going to realize this at massive scale? Now, traditionally, when we've kind of thought about it, we've kind of thought about it from hey, we can do process level optimizations. We can do a lot of microarchitecture, architecture optimizations. We can do a ton of code optimizations to squeeze out every last bit of performance. In the previous Qualcomm talk was also kind of talking about this. Song does a lot of quantization related optimization stuff at MIT and so forth. And, we're really pushing towards having really specialized custom ASICs for these things, right? But when you think about all of these kinds of flows that have to happen, the critical bottleneck is really us. As humans, there's only so fast that we can actually move, right? And as we're trying to build these really bespoke sort of systems, one of the fundamental problems we have is that it takes an incredible amount of effort to kind of specialize for a very niche area. So the question becomes, can we somehow think about, designing these embedded systems much more effectively? In fact, Bob Rao, who's a very well-renowned architect, wrote this article way back talking about embedded computer architecture and the need for automation. And he talks about several critical points down here is that embedded systems are going to be pervasive. It's pretty much like exactly what TinyML is. Yes, it's not 1991, but it's taken us a while to really get to where we're excited about. But in trying to do this, there are lots of different issues, right? You need to really address this issue of having low cost. Then you also need to have really emphasize this aspect of, you need to have really good customization, right? Because if you have specialization, then you can really cut down the cost. But that customization has its own sort of an effect, right? Which basically focuses on the fact that customization allows for achieving better cost performance, but introduces complexity in the design process, increasing non-recurring expenses, right? These increased NREs must be amortized over product volume, adding to product cost. The fundamental thing that he's talking about back then was that look, embedded systems can be very pervasive. We can have all kinds of intelligence and all that stuff on them. But the crucial issue is if it's going to be really critical to make sure, we really think of highly optimized ways of designing these systems. Now, everything we've done so far has been pretty much, the rubber stamp approach of kind of, things that we have done in the past, very much kind of repeating the same exact process. But the question today is, can AI come in to help to actually get us to kind of think about how can we design embedded systems more efficiently through, extremely complex systems that are very good at dealing with, lots of complexity. Now, we're seeing this at massive scale everywhere else, right? You talk about text, images, speech, pick your favorite sort of an area, right? There's a huge amount of data that's sitting on the internet that we're able to scrape through, build a foundation model, and then be able to do all kinds of amazing tasks. Obviously, we see this in vision tasks, right? An astronaut riding a horse in Andy Warhol style, right? You would never picture coming up with this in this sort of an example, right? But it's really possible. You can create music now on the fly just from prompting things, right? Application engineers are already using this. Copilot on Microsoft is obviously, something that people are looking at very seriously, right? Being able to have assistive technologies, right? Can you write me a piece of a website for, S&P 500 index, right? It's able to generate some bit of code. Now, code might not be perfect, but at least it does 80% of the job. And, we can do our little bit of, kind of curating things at the other end. You can even ask it to kind of go down a little bit in the lower down the stack and then say, okay, write me an architecture simulator for the most used RISC-V instructions. ChatGPT does an okay job on it. It boxes up in a couple of things that we've tried on. But fundamentally, it kind of gets these ideas. And these are not even highly fine-tuned models, right? And, at one point I was saying, like, okay, act like an RTL developer and write the Verilog code for a RISC-V microcontroller unit. It starts sketching out the template and stuff. And then if I prompt it a bit more, it actually starts trying to fill in the blanks. The key thing that I'm getting to is that, for a lot of these domains that we're talking about, if you have good data, you can actually create a potentially important foundation model that's able to, then be fine-tuned for various kinds of tasks. The question is, are we potentially on the path where we can actually, think of hardware design effectively as a way of kind of like creating a foundation model for it so that we can actually start building out, chips much more efficiently? And the reason for doing this is trying to go back and address that NRE aspect that I was talking about. If we can try and use, technology to be able to accelerate, think of it as like Amazon, right? Amazon for chips, right? In the next couple of years, we should be able to get online on a website, talk about some specifications, hit buy now, and the chip basically shows up, at your door in a couple of weeks. That's ideally sort of where we want to go, right? And now this might seem crazy from where we are today, but I'm not interested in where we are. I'm only interested in where we're going because it's a North Star that's going to get us there. So there's a lot of excitement around this. In fact, there are a couple of articles around this, even the EDA community. I'm talking about architecture. I tend to think of architecture holistically. So the EDA community has got something called EDA 2.0, which is sort of like, how do you bring in AI technologies into the domain? And that's really what architecture 2.0 fundamentally is. It's the era where we can use AI ML methods to minimize human intervention and build increasingly more complex and efficient systems in a very short time frame. In other words, I want to be able to do a prompt like this in the future, right? Act like an architect, design me a 64-bit RISC-V processor with full vector extension support, and optimize it for a 3-watt TDP in some process node that's using a plugin library, right? And while you're at it, make sure you design some sort of custom units that are dedicated for instance, just keyword spotting. Now, this is sort of like the North Star in my head. Like, the question is, can we potentially get there, right? And I think in order to be able to understand whether we can actually get there or not, I see a set of different challenges. Now, these challenges are something that, I've kind of been working with the community, the architecture community, to try and distill what are the fundamental problems that we have in this space that we have to solve in order to be able to get to that sort of a, prompting level sort of a design. So I'm going to step through each of these different challenges. I'm not going to get very low into the details because, there's limited time. But I'll try and highlight the key aspects and then talk about where things are going. So the first thing is like, just dealing with data, right? You want to touch any model. It doesn't matter how smart the model is. If you got no data, it's just useless. You got garbage data, well, that's also just a garbage model at the end of the day. The first problem when we think about hardware aspects is, unlike ImageNet, where you can just kind of go out and scour a lot of good data, right? Have, roughly good enough data to at least bootstrap the ecosystem. We don't have an ImageNet for any of the hardware design, right? Even if you do end up having hardware designs, there's a lot of proprietary information that you have to deal with. I'm simply looking at an example of what happened with ImageNet, right? ImageNet had to go back and fix a lot of the images because they hadn't really thought about privacy implications and so forth. Moreover, it's very hard for us to kind of scrape the internet for creating these large data sets that we need to actually be able to do that level of LLM-based design or something, right? We can't just go on YouTube. We can't just go on Common Crawl. We can go to Wikipedia, all these things that we have basically scoured. And that's the whole reason we're all excited about how do we squeeze this big model into a small little dinky device. That's great because there's actually data around there to work on the problem. Now, one of the ways we can try to address this problem is by simply, generating synthetic data, right? And the way you can generate the synthetic data is from like simulators. cycle level simulators or even cycle accurate simulators. But of course, if you want to generate a huge amount of data, which we know we're going to need, you have to compromise accuracy because cycle accurate simulators are very, very slow. But if you want to focus on the speed, yeah, you can crank that out, right? But that's sort of this trade-off you actually have. So we don't really fundamentally have data. That's the first sort of an issue. The second thing is there's lots of different algorithms that are out there. And the algorithm ecosystem is rapidly evolving. Just when you get settled into one type of algorithm, some other algorithm will come along, right? That says, okay, well, you should be using this algorithm now. So this leads into a bit of a confusion in the system space, which is like, how do I actually think about, using the right algorithms for the right set of tasks, right? How do I know which algorithm is best suited for what sort of a hardware design problem that I'm talking about? Even if you take one particular class of algorithms, let's say, for example, like reinforcement learning or something, the problem you have is that even within that taxonomy of space, there's a rich variety of different types of algorithms you have. Like I'm just kind of showing you a little snapshot down here, right? This is for one particular type of an RL sort of a system we're talking about, but there's so many other algorithms. And right now, there's a little bit of a confusion about which algorithms to use when. It's like people are randomly throwing darts, so we don't really have good best practices. In other words, we don't have a real good playbook. There's a really interesting paper from one of my colleagues which talks about a taxonomy of machine learning for systems problems. And it essentially is talking about this issue is that machine learning has incredible potential to improve system design, but only under certain conditions. And the key problem is that we don't have a good mapping between how do we take conventional system design, hardware design, and map that into the ML problem space. And so if you actually read the paper, one of the critical things that, Martin Mass actually argues for is that, we have to think about figuring out how to apply ML to systems in a way that you understand the characteristics of the system, and then you come up with a playbook, essentially. Now, here's an example of a playbook that he kind of put together based on his observations and building, machine learning for systems that they're doing at Google. And it's public knowledge that whatever he's talked about, right? And he's come up with a mechanism that says, okay, well, here's a rough sort of a playbook, right? So this is one of the fundamental problems. In the hardware space, this doesn't actually quite exist yet. We haven't quite sat down and said, okay, how do we systematically apply ML when it needs to be applied? Moreover, even when there are spots where it has actually been applied, we tend to focus on only a subset of the critical ways of thinking about ML for systems problems. For instance, we often think about how well does a machine learning agent actually perform the task it's been trained on, right? So you take your, your test validation splits and so forth, and then you kind of look at how is the, trained algorithm performing on the actual test set. And then we tend to worry a lot about the computational requirements. Much of, what we're hearing today and yesterday has been understanding the computational capabilities that we need in order to be able to make those agents run. But I would argue that some of the most important questions are really sitting to the right side and that no one is really, really talking about. One I would argue is how reliable are these agents in actually performing a task, right? So if I'm able to do if I'm able to solve a particular problem, like chip floor planning, for instance, using a machine learning model, then the question is, if I do it today and it gets me a certain level of accuracy or gives me a certain level of productivity boost, will it do that consistently every single time, right? Because that's going to be extremely important. Moreover, very often these agents that we create, are often very good at only the tasks they've seen. But what happens if the task distribution kind of changes a little bit? How well do they generalize, right? So these kinds of questions are not really being systematically thought about in terms of, how to go about, unlocking AI for the kind of problems that I'm talking about. Moreover, another issue is that we actually don't have proper infrastructure and tools in order to be able to systematically study this. A lot of interest in hardware companies trying to think about, how do we apply generative AI capabilities, but we don't really have open source infrastructure to actually systematically unlock this field and to actually make progress in this. Really what we need is we just need to kind of simplify the ecosystem down into what are the kind of hardware problems we want to solve? I'm just saying that it's like some sort of architecture problem. And you have, on the other hand, you have the whole ML agents that are going to have to be trained in order to be able to solve this. Much like we're talking about Llama and so forth, the being open source and that, you can use them for different purposes. We kind of need to have our own hardware sort of, hardware-oriented sort of design tools that we actually have where these agents are actually good at handling these tasks. And if you can put something like that and you create a systematic interface between the hardware side and the agent side, then you can actually, expose a set of key APIs that are standardized across the ecosystem, where everybody can, who's working on interesting problems, can, have their own black box sort of an internal thing that they're working on, but the common infrastructure that allows that sort of design space exploration or prediction or generation of tasks and so forth can actually be done abstractly. So ML algorithm people can go on and come up with all kinds of different algorithms. We basically package them up into a suite of different things that we can tap into without having very deep knowledge, because it's impossible to have very deep knowledge in both the system side as well as the algorithmic foundation side. But if we can create infrastructure that allows this sort of, bi-directional conversation to happen, then we can also create data sets, because every single time we run all these experiments, we can actually start collecting this data so that we can ultimately try to get to that ImageNet sort of a vision that I was talking about earlier. Now, I'm not going to get into the details of every single thing, but we have had a paper that we, published last year, which basically talks about this sort of an open source gymnasium for enabling hardware design, right? Long story short, it really gets at this fundamental aspect of how can we create data sets around this problem? How do we address this issue of we need data sets? That means you need to have a systematic infrastructure that will enable us to get to the data sets. Then there's a question of, okay, which algorithm is better than, all the other algorithms that are out there? We need to have an apples to apples comparison of these algorithms. So this infrastructure allows for that sort of a comparison to happen. And then you can have best practices that come out of this, because you can systematically evaluate the designs that are coming out of this infrastructure, because it's, it allows you to do the exploration, and then you can actually look at the designs and do, head-on comparisons. And of course, it's a tool, it's an infrastructure by itself, right? I'm not going to get into too many more details, but fundamentally you can think about, this particular tool is able to address all these issues. I'll leave it there, but I'm happy to talk about it offline if anybody's interested. But the idea is that you would have many of these different, instances of this ArcGym kind of running in parallel, where you're evaluating many different algorithms. Every single time you're doing these runs, you can aggregate the data, and the data is then, collapsed into a massive, large data set. And we have shown, I'm not showing results here, we've clearly shown that, if you do this method, you can start building these very large corpuses, which you can then use to start fine-tuning other models and so forth. Now, when you're working in the space, generally one key thing that is extremely important, I think, that we don't talk about because we're so caught up in the technology side of things, but being an academic, I think it's extremely important to realize that, workforce and training is going to be extremely important in understanding how we actually teach students and how we actually train our engineers to actually be able to use these tools effectively. The key word is actually effectively. Right now, what's going on is everybody's trying different things, and it's clear that there's a signal in that whole space, but we need to be able to systematically sort of, move through this. Now, I've kind of brushed through a lot down here, because it's a very fascinating area, and I'm trying to highlight the critical elements down here. And, thanks to my student, Shwetank, he's been doing a bit of exploration in space, and I'm just kind of showing you a little bit of screenshots where, we've basically been playing around with this idea that you take one big model and then effectively try and create plugins. And through the plugin, you basically try to get the, the model to actually learn a little bit of the hardware characteristics, where we've been doing some sort of custom hardware design around custom functional units, which is called CFU Playground. There's a paper on it, but it talks about how can you, effectively integrate existing infrastructures with plugins and get the models to actually use the plugins and then interface with the tools to be able to, design sort of a custom layout for something, right? So after a little bit of prompting and so forth, you could imagine he does something like this. Great, now let's run the physical implementation on our design using this guy in 130 nanometer process, right? And then effectively, it uses the plugin down here, and then it kind of generates this. And through this sort of a mechanism, we are trying to build the data set so we can actually, try and explore different opportunities and get people involved in it. The long-term goal, taking a step back from what necessarily, our group is doing, I think the idea we should really be thinking about is sort of creating some sort of LLM playground for hardware software co-design for TinyML acceleration. Why? Because it helps us, if we can create these agents, it really helps us get to that idea that we can really dramatically have the opportunity to cut down the NRE costs, for instance. And I think we should create an ecosystem where we have these, performance leaderboards that are able to, where we're able to explore hardware designs and see how well these agents are able to crank through different things. And ultimately, I think we want to get the ecosystem to be in an end-to-end flow where you have some sort of a, natural language interface, which the engineer interacts with. It plugs into some sort of tooling infrastructure, like the one I was showing you was this thing called CFU Playground. And then there's a backend where you can actually, basically integrate with open lane flows and, open source infrastructure that allows you to then kind of push a design out and basically be able to fab it out, right? So we've been doing some interesting work with pragmatic folks and trying to think of, how do we create an open source ecosystem like this? Long story short, though, this really needs a massive community-driven effort. This is well beyond any one research lab. I'm not interested in building my own kingdom. What I'm really interested in is actually solving the problem, but that needs us to bring the community together. So if you're interested in this sort of a topic, we've been trying to get the architecture and EDA community to get together to try and build this kind of shared infrastructure. Lots of academic interest is there. Plenty of companies are very interested in actually trying to be involved in this, and we're trying to build a competitive sort of an ecosystem, much like you have, Chatbot Arena and things like that for creating competitions around LLMs for other various tasks. How do we kind of create something like that in order to unlock edge AI hardware design? Now, what this kind of started out as a random crazy idea last year, and over time, it's kind of been slowly progressing and building out a bit of a community. So if you're interested, feel free to reach out. And I do want to give a shout out to the number of people behind the scenes, kind of like, helping us think through this and trying to craft this vision. So that's it. I'll say thank you. And I also do want to give a shout out to my student Shwetang, who's actually kind of, been pioneering some of this work.
Huge thanks to all of our partners. Wouldn't be possible without you. We have AI Zip, Arduino, ARM, BrainChip, Edge Impulse, which is where I work, Embed UR, Efficient, Greenwaves Technologies, Gravetti Inc., Hymax, ImagineMob, Infineon, Inotera, Nota AI, NXP, P&G, Corvo, Qualcomm, Renesas, Schneider Electric, SensiML, Sony, Silicon Labs, ST, Synaptics, Sentient, and TDK. These are our strategic partners. We also have executive strategic partners, Qualcomm AI Research, who are advancing AI research to make efficient AI ubiquitous, Sentient, who are accelerating your edge compute, making edge AI a reality, and our platinum strategic partners, Embed UR, Atrios, who deploy vision AI at the edge at scale with Sony, and our gold strategic partners, ARM, building the future of TinyML, Edge Impulse, the leading development platform for Edge ML, Infineon, driving decarbonization and digitalization together, and Renesas, who are enabling the next generation of AI-powered solutions that will revolutionize every industry sector. ST Microelectronics, who provide extensive solutions to make tiny machine learning easy. Synaptics, who are engineering exceptional experiences. And our silver strategic partners, AIZip, Arduino, BrainChip, Efficient, Greenwaves, Gravetti, Hymax, ImagineMob, Inotera, Nota AI, NXP, P&G, Schneider Electric, SensiML, Silicon Labs, and TDK. Thank you to all of you. And that's to wrap up our session here. Huge thanks to the audience and all of the presenters. We've had an amazing couple of days of insights and inspiration to go forward and build great things. So thank you so much, everybody, again, and I hope you enjoyed it.